What's going on, my friends? Dustin Stelzer with Electrician. Today we're going to talk about voltage drop. So what is voltage drop? Like, we hear this term out in the field a lot, and I think the best way to think about it is like a pressure drop. You know, like, say you've got plumbing and you're running water through it, and all of a sudden you turn the valve down a little bit and you don't have as much pressure to push all of that water current through that pipe. It's the same thing in electrical. We don't have enough of a difference of potential built up between the two things, you know, the positive and negative, or the up and the down, the opposite things in an electrical system. There's not enough pressure to push electrical current through the conductors. So it can appear in a few different ways, but first, like, what is it and like how is it experienced really? So like we just said, you can think of it as a pressure drop. So now logically, when you think about what kind of loads we hook up to things, it's usually either lighting, some kind of heat source, or there's going to be a motor. That's most things you're going to plug in or hook up. And so those three things can kind of act a certain way. Voltage drop is always experienced under a load. So you're not going to necessarily feel voltage drop unless something is hooked up and there's a load and there's a certain amount of resistance or an impedance inside of a device or a circuit for you to notice that voltage drop. So how we notice a voltage drop with a multimeter is a multimeter. Inside of it, there's, you know, a little circuit board, there's a bunch of resistors and things like that. So there's just a kind of a little load inside of a multimeter. And so since there's a 9-volt battery and everything, you're able to hook up to conductors and see the amount of pressure that's coming in one lead, going through the device and going back out the other lead that's a part of that circuit. Or, you know, another situation, like say you have a motor somewhere and it's like way off in the distance. Once you start that motor and actually energize it and current starts to flow, that's when you're going to experience that voltage drop. Same thing with like a heating element in a toaster. If you have a problem with low voltage and you hook that thing in, then nothing's really going to heat up. It's not going to work fully. And so you can kind of see once a load is plugged in, then the voltage drop is experienced. Next thing to note is that voltage drop is going to increase with the increase in distance. So the further that you run conductors, the more resistance or impedance or reactance is going to be in that circuit, because like copper has a certain amount of impedance to it, and the more length that you have, the more impedance there's going to be over a distance. So as you increase distance, you're going to increase your voltage drop. Next thing is you're going to increase your voltage drop with a decrease in the conductor size. So another issue is the amount of current that you can put through a conductor is going to change based off the size of that conductor. So if you have massive conductors, you can keep pressure from the source all the way out to the load a lot easier than if you have itty bitty tiny little conductors. It's going to drop off severely. You're not able to keep that pressure over that distance long enough. And then the last thing is that voltage drop is always going to be less on a 3-phase circuit than it is on a single-phase circuit. So we'll get into the math a little bit, explanation as to how that is the case. But 3-phase, you can kind of think it's a little bit more efficient of a system, so it's able to carry pressure a little bit better. Not a whole lot, really. I mean, we're talking kind of like relatively the same, but it is a little bit less on 3-phase systems. So how does it actually show up out in the field? Kind of covered this a little bit, but if you're looking at lighting loads specifically, lights are going to act incorrectly. they're going to do what they're not supposed to do. So basically, you're either going to notice some kind of dimming effect. On a DC system, you're going to notice that lights are brighter closer to the source, and then as you get further away from the source, they're going to start getting more and more dim. You might have some flickering happen. You might have some kind of ballast or driver or something inside of it. And because you're not fully driving that lamp, it's not going to be as bright as it should be. And so it could, if it's an incandescent lamp, you're probably not going to have a flickering issue. But if it's some kind of ballasted sort of thing, it might not actually be able to fire that. If it's HID, you might not be able to strike the ignition inside of that thing, so you might have it turn on and it might turn off, and it has all kinds of weird, like flickery, crazy problems. And then sometimes you just won't have the lights at all. If you have like a light source way at the end of a really long DC run, it might be enough of a voltage drop that LED driver just won't ignite. It won't start and excite the actual lighting element inside of that light. With heaters, heaters are not going to fully heat. Think of a toaster. You look inside the little heating elements, they're glowing orange. Well, they might not glow like brilliantly orange. They might be really dim because you're just not providing enough pressure through the resistance. The resistance is kind of like overcoming the amount of pressure. It's resisting, or it's impeding the amount of current flow that can go through it. So you just don't have enough pressure. Sometimes it's enough that it won't even heat, or it'll put off a very minimal heat to the point where you can't even tell that it's heating. So voltage drop, again, just not enough pressure to push through to make the thing work how it's supposed to work. And that is an under voltage. All of this is under voltage situation. We're not talking about over voltage. That's a whole different thing. Then the last thing, most of what we deal with is motors, vacuum cleaners, or motors, and like boat docks. When you go to lift them, they're motors. Or there's millions of different motors that you don't even realize that we use. Even drills, they have a motor inside of them. So motors can't run correctly when there's voltage drop, but the motors act a little bit differently than a normal like resistive load, because motors have inductance to them, and it's actually two different circuits. There's like the actual primary circuit coming in, and then there's the actual motor circuit, or the windings on the inside of the motor. So it's two different things that aren't actually touching each other. So it acts a little bit different. Motors, typically when you run an under voltage to them, they're going to create an over current or an over amperage situation. So basically a motor, how it's supposed to work is as it's spinning, if it spins really fast within whatever it's rated for, if it's rated for like 5,000 RPMs or something like that, if it's spinning at 5,000 RPMs, it's going to stay within the amount of current that's on that nameplate rating. So if it's a 15 amp rated motor and you're driving the correct voltage to it, and it's the load that it's actually designed for, it's not a heavier load or anything crazy like that, then you're probably going to have a normally functioning motor. But once you drop the amount of voltage that you're providing to that motor, then it can't spin as fast. So it starts to spin a lot slower. And when you slow a motor down, it's actually getting closer to short circuiting. So motors, when they are stuck, there's this thing called locked rotor current, basically meaning the rotor, the thing that spins inside of the motor, is locked in place. So it's allowing current to flow through without any impedance, resistance, reactance, anything like that. And so it mimics a short circuit, and it creates a lot of heat, and it can burn up a motor really quickly. Even just a slowly turning motor that's designed to turn quickly, it's going to have that same problem. So usually when you start up a motor, there's this huge amount of inrush current all of a sudden as it's like slowly starting to kick on. It's like a lot of current, and then it gets back and it just goes to this like nominal level where it's functioning as it's supposed to be. That's normal. That's inrush current. You can sometimes experience up to like 6 times the amount of current going through just instantaneously while that thing kicks on. So motors work a little bit inversely with voltage and amperage. So if you like dramatically have like a really low voltage problem, or say you have the correct voltage there, but your conductor is a little bit undersized or something like that, and you have a heavy load, and you put a heavy load onto this motor, if it's a heavier load than it's designed for, that motor is actually going to smoke. It's going to burn up because, again, it just can't spin fast enough. You put a really light load on the same motor and it might go just fine. So that's voltage drop. It's under voltage is going to create too much current, which is going to melt the insulation around those conductors and probably overheat that motor and burn that thing up. You might actually start to see smoke coming out of it. So a lot of times when you have a motor that's smoked and you notice there's a long distance down there, or you notice that there's really small conductors over a long distance, you can immediately be like, okay, this is a voltage drop issue. This thing should be lifting just fine. It's not lifting, or this thing should be turning on, but it's really sounds like it's struggling and it's hot. Like that thing is getting really hot. It could be a voltage drop issue. But if it's not a distance thing, It could just be that the motor's bound up, the bearings aren't greased or something in there, so it's just not allowing, again, it's just not allowing the speed to happen. So motors are tricky. There's a lot of different things to motors to understand about it, but essentially under voltage in all of these situations is voltage drop. You're just not providing enough pressure to it for it to function properly, so it's not going to function properly. So that's something to think about with voltage drop. Some examples of voltage drop, there's actually two different calculations. You could even use Ohm's law for voltage drop to try to figure out if you want to do like a simple voltage drop calculation, but it doesn't take into a factor some of the things. There's like a K factor, which is a coefficient, basically, like copper has a certain resistivity, and aluminum does as well. And so they have these little things that you're able to put into a calculation to figure it out. Then it factors in the exact wire size. So it's a lot more precise method to use these formulas than just using Ohm's law. But if you were to use Ohm's law and you used it correctly, you could get very close values. They're just not going to be quite as precise. So the single phase voltage drop, you're going to have this is voltage drop 1, voltage drop 3, three phase, you get it. But a single phase voltage drop, you're going to have a calculation that looks like this. It's 2 times K, which K for copper, it's just a flat number, it's 12.9. That's all you got to remember. All your tests and all, out in the field, if you're dealing with copper conductors, you're going to use 12.9 for the K factor for a copper wire. If you're going to be using aluminum, it's 21.2. So just remember those two numbers, 21.2, 12.9. That's always going to be your K, just depending on what you're using in the field. I is going to be the current or the intensity of the flow of current going through a conductor. So it might be a 15 amp rated motor. You're going to put 15 amps for I. D is going to be the distance. Some people actually put L, so 2 KIL over circular mils. That's not centimeters, by the way, it's circular mils, but it's either 2 kid or 2 KIL. It doesn't matter, however you want to remember it. But your distance, and you're not figuring out distance both ways, you're just figuring out what your total distance is going to be. And then underneath that, circular mils. So conductors are actually rated in circular mils. So if you have like a 250 MCM or a 250 KC mil, that means it's 250,000 circular mils. And that's how they figure out the actual area of that cross section of that conductor. So that's your whole calculation. What you notice on a single phase and a 3 phase is that there's a difference of only the number before the rest of the formula, right? Everything in 3 phase, we always use the square root of 3 because of the phase angle of how those things are being generated, how those phases work, and which one is sharing the load at any given time. And because there's 3 of them and they're 120 degrees apart, we use this thing called the square root of 3 to represent that mathematical relationship. So you're going to notice 1.732 times a bunch of stuff divided by some stuff, and then in single phase, you're going to notice 2 times a bunch of stuff divided by a bunch of stuff. 2, you can think of that as like one way there and one way back because you have a 2 conductor circuit. So automatically you know that the numbers are going to have a certain relationship and it's going to be the same no matter what. These numbers, because you're multiplying this whole thing by 2 and this you're only multiplying by 1.732, is why 3 phase is always going to have a lower value. It's going to have less voltage drop, but not very much, like a fractional amount difference. And it could be the difference between like a 2 volt drop and a 3 volt drop. You know what I'm saying? They're not like massive figures that you're going to come across if all other numbers are the same. But those are the voltage drop formulas that we use out in the field. Here's some examples. So kind of messy, I suppose, but like say we have a single phase environment, and we know we're using a copper conductor, so we use 12.9 for our K. We've got 2 because it's 2 times K. I is 20 amps, so say we have a 20 amp load, not a 20 amp circuit. Whatever your load is running, the amperage of that load is what you would put for I. And then your distance, say we have like a 300 foot distance that we're trying to cover. There's going to be some voltage drop here. So 6530, if you look up in the code book in chapter 9, table 8, it actually shows all of the different circular mils for all the different conductors. So number 12 copper, we're going to say that we ran number 12 because it's 20 amp circuit, right? So it's 6530. So if you do the math on all of that, on this 300 foot circuit trying to run a 20 amp load with copper conductors, number 12 specifically, you're gonna notice a 23 volt drop over 300 feet. So now you realize like, oh crap, I was plugging this 120 volt thing in, it's rated at 120 volts, this vacuum cleaner, but now I'm running it at like 96-ish volts. That thing's gonna be under voltage. It's not gonna work properly. It's not going to be able to spin as fast, so you're gonna have more current going through it if it's a vacuum cleaner. The thing's gonna get really, really hot and probably burn up. So that's a big, big, big voltage drop for a 120 volt circuit. Or even a 240 volt circuit, because if you're talking about a motor load, they're a fixed load, fixed wattage, or fixed volt amps. But essentially, if you ran that same like 1 horsepower motor, the horsepower is fixed. The amount of power that thing can generate, either 1 really big horse or 2 little horses that equal 1 big horse, it still doesn't matter, 120 volts or 240 volts split between 2 different things. It doesn't matter because it's a fixed horsepower. You're only getting the power of 1 horse. Doesn't matter how many times you chop the horse, it's just 1 horse. So it doesn't matter if you run it 240, it doesn't matter, if it's dual rated and you run it 120 or 115 if it's rated that, you're gonna get the same voltage drop through the system because that thing can only spin so much and it only produces so much power. So 3-phase, same exact thing. Just notice that the values, we got 2 times, it's all the same loads, but this is 1.732, so we still got 12.9 K factor, we've still got 20 amp load over 300 feet, and we're using number 12 copper. So you'll notice it only drops 20.5 volts. So again, not very a huge difference, but with 3-phase, it's always going to be slightly less because it's sharing everything between all 3 windings. So it's just a little bit more efficient at handling something like this. Basically, understand it that you can keep the pressure to the load or through the system a little bit better. All right, so I don't know why I had to draw this. I think that's pretty self-explanatory, right? But I think I drew this way before I drew the other things. So anyways, just remember lighting out in the field. If you notice it's dim or you notice that it's maybe flickering or acting crazy, it could be a voltage drop issue. With heating, you're gonna have heating elements inside of something that are producing a lot of heat if everything's running the way that it should be and you have your correct voltage. But if you're under voltage and your voltage is being dropped, it's gonna be dim. I'm not putting out very much heat. And then motors, just remember, they're gonna be spinning like crazy, spinning fast, working great, lifting the loads that they're supposed to be, or driving the thing or moving the thing in the way that it's supposed to be, and they're not gonna be overheating. But if you notice overheating and that it seems like whatever you're driving, that motor seems like it's really struggling and it's producing a lot of heat, it's probably an under voltage situation, unless there's obvious visual signs of it being like something's bound up with it or something's in the way and it's not letting it spin. Then in that case it's not going to be voltage drop. But these are things to look out for. Now in all 3 of these situations, it might not be voltage drop, right? Like you could have lighting that's dim, you could have like a ballast that's going out, you could have an HID fixture in a light pole that has a capacitor that's burning out, you could have the igniter that's burning out, you could have a bulb that's about to fail or it's at the end of life if you have like a high pressure sodium bulb or something like that. So that doesn't mean that that's what the problem is. It's just to say that if you notice, like I'm at this huge parking lot and there's all these like light poles, they're kind of acting crazy and they're brand new and we just put all this wire in, but holy shit, I didn't really realize like how far away from the panel this is. And we put a bunch of them on one circuit. You can start to think and diagnose when you're doing service work out in the field like that. And obviously just motors too, like, like I said, it's not just under voltage that can make something. Over voltage can make something happen too. It can make a motor spin way more than it's supposed to. It's still gonna heat up, still gonna act crazy. You're probably gonna notice the load is like out of control, because there's too much voltage, putting too much pressure through a motor that's not designed to spin like that. So it can overheat, burn up, same kind of thing. So there's like 50 million reasons why any of these loads could be doing what they're doing. But again, I just wanted to show with voltage drop kind of like what's going on and why you could be experiencing some of these from voltage drop. Now, I have a couple of examples of voltage drop that I've run into. There's one for DC and one for AC. So the first one was recently I did a job where we had AC power out at the street. We had to run an underground and go over to a boat dock, and that boat dock was 475 feet away. I was told from afar that it was 370 feet. So I just had a 500-foot roll of number 4 aluminum that we like used for like T-poles and stuff, or like temporary power, you know, putting a possum out in the middle of a building, running it off a T-pole. So we just kept like rolls of that around. I'm like, number 4 aluminum, that should be fine. Did a little calculation. I figured, all right, on this boat motor that's lifting it was a 15 amp load. On its nameplate, it actually said 15 amps, 115 volts. So I was like, that should definitely lift this boat. Now this boat's probably 6,000 pounds, maybe like 6,300, 6,200. And then I think there's like 600 pounds of fuel as well. So the dry weight and the wet weight are way different. So it's damn near 7,000 pounds to lift this boat. And I've got a voltage drop of, you know, almost 400 feet. So I just ran this wire. It was all supposed to be temporary anyways. Like, we're building a house on this property. And so for the time being, it's summertime Texas. This guy bought a brand new $300,000 Super Air Nautique. Dope boat, by the way. Speakers, the whole 9 yards. But he was so excited to just like party on the lake, have his friends out there while he's building his house. So we're like, all right, let's just run some temporary power down there. We'll lay it on the fence, you know, along the outer perimeter of the property, and just get power down there so he can lift his boat up and leave it there. And then when he wants to come back, he can lower it and just go drive off. With the full intent that later I was going to come back and run solid copper conductors that are much larger size, so that it would, you know, it was our permanent solution. Because we were actually, there's like a boat house down there, not like a boat house on the water, but like a house kind of thing where they could store all their stuff and kind of like party and stuff like that. And then it was attached to a dock. So we had an actual panel that fed all the plugs and everything. So I wanted to feed it, you know, like a good 100 amps to that panel. And then there was another panel below that kind of ran a bunch of other stuff in the boat lifts. And so I wanted to provide enough power down there. But for the time being, I just needed to get one of these lifts to work. So I was like, number 4 aluminum should be plenty. I even checked with an electrical engineer, friend of mine. I'm like, hey, this is what I'm thinking about doing. Number 4 aluminum. I don't think there's any problem with that. You think we should go larger? And he was like, no, I don't see any issue with that either. I mean, you could go larger. It would only help, but I would, you know, I'd feel comfortable with number 4. That's fine. So I was like, all right, went out, ran this thing, tried lifting that boat, and it was just like it did not want to lift at all. And I'm like, whoa, is the motor messed up? You know, like, I get it. It's only 115 volts, but it's a 15 amp motor. And yeah, it's a heavy boat. So I called the manufacturer of the motor and I'm like, yo, this is kind of what I'm experiencing just before I like undo everything that I did. Is there any chance that the gearing is wrong and it's just not set up to like geared correctly to lift this boat? And they're like, no, we have these models of boats. We match them to an entire package, the gear package, the motor, all of it comes together, and people buy thousands of these from us every year. Like, this is definitely not a problem with our equipment. So there was 2 of them, right? So I was like, all right, let me just try hooking up the power to the other one and see if it does the same thing. Move the boat over, tried it, same thing, it wouldn't lift. I'm like, fuck. All right, this is definitely a voltage drop issue. So even to test it, we pulled a generator out there, just a portable generator, hooked it up, lifted just fine with the boat on it, no problem. So it verified that's definitely still a voltage drop issue. So I was like, damn, like on my calculation, it should have only dropped about 4 volts. So it should definitely have the power to pull this boat up out of the water and drop it down. Now, it was lifting, it just wasn't lifting consistently, and it would lift and it seemed like it was really straining and it wouldn't get it all the way up, it would just stop. And then if you tried to raise or lower, it just wouldn't do it. So I was like, all right, if we keep fucking around with this, we're gonna burn up the damn motor. So what I did is I took all of that wire out, brought it back to the shop, and I went and ordered actual like copper conductors. And I went all the way up to 3/0 copper. And I did a 2/0 copper neutral, I think, but that feeds everything down there now. So we had plenty of size. And so once we got all of that run, and actually, to be fair, before I even ordered the wire, I went back and verified the measurement because I didn't do that the first time. I just trusted somebody's word on it. It was actually 475 feet. So with that, plus we had about another 100 feet from there. We had some number 4 copper SOOW. So we increased our size a little bit, going like transitioning to get under the dock and feeding one of our panels. And then from there, we had number 12 circuit. We just had some like Romex that was going over and feeding these docks. But between all of that, we probably had an extra 100 feet. So it was probably 575 feet all said and done. So that changed everything drastically. So that put a situation where the boat would have lifted just fine to putting it on the verge and trying to work and having to overwork because there's not enough pressure for it. And again, these are motor loads. So we were applying too little of pressure to a motor that's trying to lift something, meaning the motor is going to be going slower. So I was pulling my ammeter out and it was saying like 60 amps on this number 12. It was drawing so much current because it just could not keep up. It couldn't spin enough because there wasn't enough pressure to cram into that motor to make it spin like it was supposed to spin. So anyways, once we got all of the copper 3/0 conductors, we're talking, like big wires, that completely deleted the voltage drop. And so it lifted all the boats just fine. So that was a real world scenario where voltage drop is an issue. And sometimes it's kind of a moving target. You can't actually figure out what's going on because the nature of the load is going to make everything in that situation different. If we were pulling up a jet ski, we wouldn't have had the same issue. That voltage drop would have been a lot less because the load was a lot less. There's less impedance at that motor. So it probably would have lifted that fine. But right now we were at the top edge of where that motor was rated for. And it was like right at 7,000 pounds. So in that situation, again, it kind of like exacerbated the problem because we were lifting something that was at the upper limit of the capabilities of that motor. So the load is always going to change how voltage drop appears. Just as an easy example to show what we were running into, I had a 120 volt circuit that was coming from a panel. I had a 15 amp rated motor that was trying to lift a 7,000 pound boat. I ran number 4 aluminum. So let's see what the actual voltage drop for that should have been. So on a single phase AC system, we have our single phase formula. I used 2 times 21.2 because I ran number 4 aluminum. It was a 15 amp rated motor and it was fully loaded. So I'm kind of assuming that it's actually gonna draw 15 amps and not like 12 or 13. 475 foot distance. And then number 4 aluminum is a 41,740 circular mil conductor. So you do all the math and you end up getting a 7.2 volt drop. I didn't really think that that was all that much. Actually, when I was told it was 370 feet, this number was even smaller. It was like 4.75 or something like that. So I was like, oh dude, I'm not worried about that at all. The next situation was a DC voltage drop. So DC, AC, they both experience voltage drop, but with AC, you're experiencing it in the entire circuit at one point because the whole circuit is just shaking back and forth and vibrating essentially in an AC circuit. So you have the same kind of problem throughout the whole circuit. And with DC, you have the problem of only one direction, current's traveling in one direction. So the further you get away from the source, you're gonna have lights that work and then they're gonna start like not working so well. And then they're eventually gonna get to the point where they're not working at all. And so you'll see this crazy thing where you've got like a whole bunch of lights that are going from bright to dim, and each load is kind of sucking up a certain amount of that pressure and not letting the pressure go all the way through the circuit. So I did my first ever voltage drop job. I did a job. I didn't even know about voltage drop. I'd kind of heard people talk about it, but I had no idea. I was probably still an apprentice and I was doing side work. Somebody hired me to put some landscape lighting on. It was 12 volts, but in their front yard. And I'm artistic and aesthetic and I love like making things look really cool and custom lighting and all of that stuff. That's my jam. So I got out there, put this transformer on the wall that I got from like Home Depot. And then I started asking, I'm like, all right, where do you want all these lights? Like what kind of effect do you want to go with? And they're like, we just want to trust you, like whatever you think. And I'm like, dope. So out of their front door, they got like this curved driveway and I put all these lights that like stand up and shine light down all the way around it. There's probably like 13 of those. And then ran all the way down the driveway with more of them. And then we had a whole bunch of trees that they had like multiple lights shining up into the trees, and they had some trees where they wanted things shining down and like just these cool like bush features and shining stuff up at the house. I probably had 30 lights on this damn thing on, I don't know, probably like a 300 watt transformer. Or no, I think it was probably a 600 or a 900 watt transformer. I think I did get enough of a size of a transformer, but I definitely had way too many loads. So that's what happened. I went and turned this thing on, and I noticed as I'm walking away from it and I start walking down the path of like the first light I put in and then the second one, everything was working. I'm like, yeah, like I'm so proud of myself, And then I start getting down to like the 10th one and it's like barely lit, it's like half the amount of light. And I'm like, whoa, that's kind of crazy. Like, why is that one so dim? And I kept walking and they get dimmer and dimmer and dimmer on all the way to the end. I had like 8 lights that just weren't working. And I'm like, what the fuck? Like, did I mess up a termination somewhere? Like, why is this happening? And I couldn't figure it out. So I called my boss at the time and I'm like, what's going on? And he's like, welcome to voltage drop, my friend. So I learned right then and there. I ran one set, just underground conductors. It was number 12 stranded. That was all. To run all of those lights on that small conductor over probably a couple 100 feet of distance with DC loads and far too many loads on a single circuit. So I learned, okay, well, that's how DC works. So the only way to rectify the situation was to double up the wire or to pull all the wire back out of the yard after I had already like backfilled everything and put bigger wire. So, well, doing double the amount of wire does the same thing, right? You have 2 conductors, or now you have 4 conductors, and you've just increased the surface area of the conductor size so you can actually pass more pressure through the system without that loss, that pressure drop happening or that voltage drop happening till like later in the circuit. So we could figure out on this DC circuit, voltage is much lower and the distance is a lot lower than our last example, but the amount of distance is still gonna be so great that because of the low pressure system, it's not much of a pressure system. So after that distance is gonna really exponentially ramp things up. So that voltage drop that I was experiencing on the low voltage lighting was using copper, so 12.9. There was 18 1 amp lights, so 18 amps worth of lighting. That's a lot. 150 foot distance, and then we used number 12 copper, so 6530 circular mils. When you add all that up, that's 10.6 volts. So that means by the end of that circuit, on a 12 volt circuit, we're dropping 10.6 volts. We're almost dropping all of it down to nothing. And in reality, I probably had like 25 or 30 lights out there, which is why the last like 8 or so were not even lit. There was just no voltage at all left over. There was 0 pressure at the end of that circuit. There are a couple of things in code, branch circuits and feeders. So in branch circuits in 210.19a, informational note 3 says conductors for branch circuits as defined in Article 100, sized to prevent a voltage drop exceeding 3% at the furthest outlet of power, heating, and lighting loads or combination of such loads, and where the maximum total voltage drop on both feeders and branch circuits to the farthest outlet does not exceed 5%, provide reasonable efficiency of operation. So they're saying that if you have a branch circuit or if you have a specific conductor, just make sure that like the branch circuit portion of it only has a 3% voltage drop, and then the feeder portion mixed with the branch circuit should only have 5% total voltage drop. So if you go to Article 215.2a, we're specifically talking about feeders. And the informational note number 2 under that says conductors for feeders as defined in Article 100, sized to prevent voltage drop exceeding 3% at the farthest outlet of power, and it continues on to the whole 5% thing. So if they're calling it a branch circuit, they're saying just for that branch circuit you don't want to have more than 3%. If they're calling it a feeder, same thing, not more than 3%. But the total from, say, like the service panel through a feeder that feeds to a sub panel in the garage somewhere maybe, and then all the way out to the actual load or receptacle, light, whatever it is, that whole distance shouldn't exceed 5%. Again, just a recommendation. One thing you need to pay attention to is most loads will actually have a rating of plus or minus a certain percentage of voltage. So some motors that you get, CNC machines, things like that, they'll actually say on the nameplate, this is 230 volt equipment plus or minus, or plus 5%, minus 10%, whatever. They're, plus or minus 5%. But they all have like a little bit of a variance because every power system is not going to be the exact same voltage. Some places, some buildings are they're gonna provide 240 volts, but you're going to notice it's like 248 when you actually test it, or it might be like 236 or something like that. So there's a little bit of fluctuation in voltage. So all equipment is manufactured saying the final voltage, when you hook this thing up to it, these wires that you are hooking up, and you test them right here, plus or minus 5%. Other than that, you're probably going to destroy the equipment, or there's a potential that you could. So just be mindful of that. There's some other places in code that actually say it all says the same thing, but there's one for conductors, there's one for branch circuits, there's one for feeders, and then there's another one for sensitive electronics equipment in like 647, I believe. So each one of them pretty much says the same thing, though. It's kind of like, make sure when you're hooking stuff up that you think about voltage drop, but we're not going to throw a code in here that makes you actually have to like adhere to a voltage drop code. It just, there's nothing like that in this code book, just recommendations. So hope that helps. Before you click off this video, if you like little like calculation thingies and you want to kind of dive deeper into that, check out this video. I actually did a video on like transformers and how to size transformers and different 3-phase calculations and single-phase calculations for transformers. If you want to know more about conduit fill, there's a lot of like, you know, math in that and figuring out what size conduit, which size conductors and stuff. It's a pretty dope video. So love you crazy people, and I'll see you in the next one.